guys, good afternoon.
Today, we are about to explore the world of chemical reactions.
But first, let us introduce ourselves. I am John Rexiconas Bacacao.
And I am Hannah Jane Arportas.
And we are from Grade 11 Curiosity. Today, we are going to tackle two lessons, the reversible chemical reaction
And the equilibrium constant.
Let's go!
Lesson 6.1 Reversible Chemical Reaction. The main idea for this topic is about a reversible chemical reaction reaches a state of equilibrium. Example question: how is equilibrium achieved? Chemical kinetics describe how fast or slow a chemical reaction occurs. Chemical thermodynamics tells whether a reaction is spontaneous or not. However, for all chemical reactions described in these two disciplines, only two outcomes are possible. Number one, reaction will either go to completion or it will reach to a state of equilibrium. Theoretically, all chemical reactions are reversible. Some are only preserved to be irreversible because of the forward of reaction is too fast while the reverse is too slow to be detected.
In such cases, although the reaction is only attains to near completion, it is practically assumed to proceed in the forward direction. Other reactions are easily to observe and describe as reversible because they have a appreciable rate of reverse reaction. This type of reaction does not go to completion. Instead, both forward and reverse reactions occurs at equally significant rate.
Now we have here the pillars of science. Norwegian Scott Maximilian Goldberg and his brother-in-law Peter Wage, they proposed the law of mass action, which states that the ratio between the concentration of the reactants and products is constant at equilibrium. Wage was a chemist, while Goldberg was both a chemist and a mathematician. They both served as chairman of the Norwegian Polytechnic Society. Example of reversible reaction. One example of a reversible reaction is the reaction of hydrogen gas and iodine vapor to form hydrogen iodide. The forward and reverse reactions can be written as follows. As we can observe the forward reaction, it is balanced equation. And then for reverse reaction, still balanced, but the product and reactants are reversed. That is an example of reverse reaction. A good example of a reversible reaction is the decomposition of colorless dinitrogen tetroxide gas into the brown nitrogen dioxide gas. We can illustrate that the balance equation is just a reversible reaction.
Our next topic is all about the equilibrium constant. The equilibrium constant of a chemical reaction is the value of its reaction quotient at a chemical equilibrium, a state approached by a dynamic chemical system after sufficient time has elapsed at which its composition has no measurable tendency towards further change. To understand more about the equilibrium constant, let's relate it to a situation. Here we have two cities, named City A and City B. These two cities are connected by a highway. Let's say that City A has 1,000 cars while the City B has 2,000 cars. In every 1 hour na ay 10 cars ang travel from City A to City B. At the same time, naasay 10 cars ang travel from City B to City A. So, ato ang forward rate is equal to 10 cars while ang ato ang reverse rate is equal to 10 cars. The concentrations of the reactants and products remain constant at equilibrium. Thus, the ratio of the equilibrium concentrations of these substances should also be constant. Consider a reversible reaction with a general equation, where A, B, C, and D are the coefficients of the substances, and Kf and Kr are the rate constants of the forward and the reverse reactions respectively. At equilibrium, rate forward is equal to rate reverse. Using the rate law, Kf, absolute value of A, raised to the power of A, and absolute value of B raised to the power of B is equal to Kr, absolute value of C raised to the power of C, and the absolute value of D raised to the power of D. The equilibrium constant K is expressed as K is equal to Kf over Kr, or we can also say this as the products over reactants. Based on the equation, a high K value with the double angle bracket 1 means that there are relatively more products than reactants at equilibrium. This indicates that the formation of the products forward reaction is highly favorable. A low K value, double bracket 1, is less than 1, on the other hand, places the equilibrium far to the left, indicating that only a small portion of the reactants are being converted to products where every portion of the products that are being converted back to reactants. For the nitrogen tetroxide yield nitrogen dioxide system whose equilibrium constant was experimentally determined to be equal to 4.6 times 10 raised to the power of negative 3. As you can see in your screen, this symbol represents the reversible reaction. The equilibrium constant expression at 25 degrees Celsius is written as K is equals to nitrogen dioxide raised to the power of 2 over nitrogen tetroxide is equal to 4.6 times 10 raised to the power of negative 3. So, nakakita mo, di ba, ang equation is equal to product over the reactants.